So looking at page 72, a little bit more with arithmetic and geometric series. We didn't really do much with arithmetic series, or we didn't do anything with it on the previous page because there really isn't much to do with it because there's only the rare case where an arithmetic series would converge. So that would be only the instance in which A1 and D are both equal to 0. All right, so arithmetic series follow a linear equation. And so linear equations, if you think about it, when do they ever converge on a single value? The only time they ever do that is when in terms of a sequence. Sorry, I wanted to be clear about this. In terms of a sequence, they converge on a single value whenever it's a horizontal line. But in terms of a series, if you're adding them up, the only time that would ever happen is if it's a horizontal line, and specifically that horizontal line has a value of 0. Because even if the horizontal line has a value of 1, if you add 1 to itself infinitely many times, it's going to continue to get larger and larger. All right, so there's only that one rare instance in which an arithmetic series would ever converge, and that's only the case when it's the line y equals 0. All right, so the geometric series is really our focus. So we have a test that allows us to make a determination of whether or not it converges. Now, in most cases, as you'll see as we move forward, we only are really going to care about whether a series converges versus when it diverges. We don't always care about what it converges to, because if you think about it, knowing that something is going to converge onto a particular value tells you that you're not wasting your time trying to find the value that it converges to. And it may involve some advanced techniques, but it may even involve a computational technique, right? In which case you're getting the support of a computer, and software, right? So if you've ever run a program and had the old spinning pinwheel of death, you're like, oh, there's a logical problem in the software, and so the computer is having maybe a circular logic issue, and it can't arrive at a solution. All right, so maybe that's the case of it's just faulty software, but maybe it's a case, or it could be hardware. Maybe you should close a tab every once and again. I don't know, but it could also be the case that it's a divergent situation. All right, there is a flaw in the logic. All right, but if there is a convergence situation, if there is a solution to be arrived at or to, then the software or your rote computations will eventually get you there. It's just a question of whether it's worth it to spend that time. Right? So we look for convergence and divergence going into a problem to make a determination of whether it's worth it to spend the time on that problem. All right? And so recognizing the type of series that you're dealing with is really important, because if you know what type of series you're dealing with, you're going to be able to more easily identify what approach to take. All right. So this is rehashing the problems on the previous page. We now know that we can represent this first series as the sum going from n equals 1 to infinity of 3 times 1/2 to the nth power. All right. And you can verify it a bunch of different ways, technology-wise or by hand. But what we're looking at are the a sub 1 and the r values, but specifically whether or not the r value has an absolute value that's less than a 1 or greater than or equal to 1. All right. So is the absolute value of r less than 1? The answer is yes. So therefore, this series, normally I wouldn't write out the whole series, but because I could just copy paste, converges. Now we do want to be prepared, if the question asks us to determine what it converges to, but that's not what the question asked here. So we're just going to say that it converges. As opposed to the second one, Now this one, we want to get it in the appropriate form first. All right, so there's not much to do in terms of getting it into the appropriate form because, we know, and I'll just bring it back because it is the same one that we did on the previous page. The first entry is 3/2. All right. So it's like, okay, well, if the first entry is 3/2, what is it going to take to make that first entry a 3/2? You know? So what would the a sub 1 value have to be? Well, it's kind of already in that appropriate form. Because if that a sub 1 value is a 1, then plugging in a 1 for n will get us a 3/2. Plugging in a 2 for n will get us a 9/4. 9/4? 2 for n. 9/4, yeah. All right, it's just 9/4 and 3.75 are the same thing. So let me just make sure I typed in the right thing. Oh, don't mind me. I just expanded a sequence. I didn't find a partial sum. This gives you a partial sum. Aha. So let me just do it. I'll do it the old-fashioned way. All right. By using the sequence mode in our calculators. All right. So that would be 1 times 3/2 raised to the nth. Then into the table we go. There's my 9 and 9/4, right? Yeah, so that's 2 1/4. All right, so we're good there. So now that we have the appropriate form, we could pull out an a sub 1, which we really don't need, except to guarantee to ourselves that we're in the right form. All right, r is equal to 3/2. And again, I would ask myself, I guess I don't want to copy too much. Is the absolute value of r less than 1? The answer is no. And so therefore the sum from n equals 1 to infinity of 3/2 to the nth power is going to diverge. So it diverges. All right. So little spacing issue in the box here, the nth term test for divergence. You'll see it just looks a little weird, so I'll fix that at some point. So if the limit as n approaches infinity of a sub n does not equal 0 or some non-existent value, then the series diverges. All right, so that's a weird one. So if it does not equal 0 or DNE, then the series diverges. So the notation here, like at the bottom, not notation as in like a sub n, notation as in like condition or caution. This does not say that if the limit is equal to 0, the series converges. It only proves divergence. That's why it's called the nth term test for divergence. All right. If the limit is equal to 0, then we don't get anything out of it. Then we have to use some other kind of test. All right. But this nth term test for divergence is a useful test, at least to get you started. All right. But I can tell you, and this is very important, students do this all the time. They fall in love with this nth term test, and they pretty much ignore everything that follows. And so, yeah, on a 10-question test, they're good for one problem. You know, so it's not going to serve you very well to just learn this one test, this nth term test, and be done with it. There's a reason why there's 20 more pages in the packet. All right. But if I wanted to try to apply the nth term test, let's say for part B here, I could be looking for the limit as n approaches infinity of a sub n. Now what's a sub n? A sub n is the argument within the summation. Right? So 3/2 to the nth power. All right. So, well, that's equal to infinity in some capacity, right? It's just like, what kind of infinity is it? But it's exponential. So 3 over 2 to the infinitieth power is going to be infinity, right? So it's going to increase without bound. So again, let's just read through this. If the limit is not equal to 0 or dne, all right, then the series diverges. All right, the limit is not equal to 0, so the limit as n approaches infinity of 3 over 2 to the nth power is not equal to 0. And we do get into that little gray area there, where it's like, well, infinity, it's like, that means that there's no limit to how high it can go. Doesn't that mean that the limit does not exist? Well, the limit does not exist means that there's some sort of contradiction. You know, if you think about the limit coming in from the left side and from the right side as you approach a single point, how they go to different places, that's the case where you're talking about a limit not existing. You know, other opposite sides of an asymptote. You know, you'd have something along the lines of like maybe negative infinity coming in from the left, positive infinity coming in from the right. You know, if you're looking at, let me put it in function mode. This is one of those cases where I realized that nobody could see my hand waving. But if you come in from the left, oh, that was fun. Coming in from the left, see it's going down to negative infinity. Coming in from the right, it's going to positive infinity. We have a disagreement. If the y values don't agree at a certain x value, then the limit does not exist. All right. But if I have something like 1 over x squared, see how coming in from the left as I approach 0 and from the right, they're both going to infinity, so the limit would be infinity. All right? So the limit does not equal 0, the limit does not equal dne, so therefore the sum as n approaches 1, the sum from n equals 1 to infinity of 3 over 2 to the nth diverges. So that's an example of the nth term test, all right, for divergence. Now you could try it for part A, and just see how that goes. It's really kind of along the same lines, with the idea being that this piece, if you plug it in, that's going to go to 0, all right? 0 times 3 is going to be 0. Now, that's the weird part. It just so happens that it converges, but just because the nth term test gives you a 0 does not mean it must converge. It means it can converge. We would need to do something else, and that something else is the geometric series test.